Okay, so the next talk is by Vishwas, and he'll talk about sparse polynomial factorization.
Okay, thank you everyone for showing up. So this is joint work with Shubhangi, my advisor, and Ilya Volkovich. And I've changed the title slightly, which I think does more justice to this talk. Okay, so the question is really natural. So it's you have a polynomial in n variables, and there is this slightly different restriction. So instead of having total degree bounded by d, I talk about individual degree bounded by d. It's something which we usually study. So this is slightly different, but it's just a new parameter. So sparsity of a polynomial, which I denote by this norm of f, is actually number of monomials with non-zero coefficient. Again, well-studied object. So a simple example, if you look at this polynomial, sparsity is just 4, and the individual degree here is 3. Okay, good. So if individual degree is bounded by d, the sparsity can be as high as d plus 1 to the n. So exponential in n. But polynomials which have like poly n, poly d types monomials, we call them sparse polynomials. And it's a really natural complexity measure studied in lots and lots of works. Okay, so a very natural classic question asked by von Zurgathan and Kaltofen was, are factors of sparse polynomials sparse? So they looked at this really simple example which is inspired by a geometric progression formula. It's like if you look at xi to the d minus 1, then this thing 1 plus xi square up to xi to the d minus 1 is actually a factor of xi to the d minus 1, and if you sort of boost it by multiplying over all variables, this gives you a sparsity blow up. So if you see, the sparsity of f is 2 to the n, sparsity of g, which is a factor of f, is d to the n. So you can see a log d blow up. And looking at this, they basically ask this question: are sparse polynomial quasi-polynomially closed under factoring? Are all factors of sparse polynomial just quasi-polynomial sparse? So they conjecture this and basically ask this question: what can we do? Okay, so this is like a rational or complex example.
What's the conjecture?
So the conjecture was that this is actually true. That you can. So I will not say that it's a conjecture. It was like more of a question and a conjecture together. Okay, so but over finite fields we can do much more crazy stuff. So over finite field, if you have the characteristic to be p, and if you have this polynomial which is like a power of a linear form, which because of the Frobenius action looks like this. So sparsity of f is here just n, but if you look at any power of this linear form where d is less than p, this is completely dense. So here you can see an exponential blow up in sparsity in terms of the individual degree. So over finite field there can be exponential blow up in terms of individual degree. Okay, good. So okay, let's ask what are the previous works known. So these are all how dense can a factor be as an example. Can you tell me a global bound? So what are all the works on this? Actually not much. So we know very special cases like d equal to 1, d equal to 2, which somehow use the fact that the factor here are variable disjoint or somewhat variable disjoint. And there was a beautiful attempt by Dwyer and Oliveira in 2015 where they sort of claim that factors of sparse polynomial are actually quasi-polynomial sparse with beautiful ideas, but sort of their approach was field oblivious, and because of it being field oblivious, Volkovich said, okay, look at this example, what do it does, and this simple example somehow completely messed up this whole beautiful idea of Dwyer and Oliveira. But
why is it? So you're saying, what is the factor of what?
So G divides F, right? Because this is actually summation xi to the p, but over finite field fp it looks like this. So we somehow get inspired by their work and do something, and I'll show what exact thing they showed afterwards. Okay. So, but if you, instead of looking at this question, are factors of sparse polynomial sparse, if you look at this more general question, are factors of low complexity polynomial of low complexity, quite a lot of work was done on this. So yes, in all these cases, Kaltofen said for VP, factors are indeed closed. For constant depth circuit, Raphael showed that if you assume small individual degree, they are closed. For VNP, quite recently, Datta Saxena Sinababu, Cheening, Rinal, and Noam Solomon showed that VNP is indeed closed under factoring, and ABPs and formulas are quasi-polynomially closed under factoring. So okay, in some sense, if a circuit class is big enough, it's easier to show that it's closed under factoring, because all the computation you require can be indeed done in that complexity model. That's why this sparse polynomial question is somewhat harder. Okay. Good. So let me tell you our results. So what we show is, if for all fields, if f is S sparse, then its factors are s to the order d square log n sparse. So I show you an example where the blow up is s to the d. This is slightly weaker than this. It says s to the d square log n sparse. Okay, so this is the first non-trivial bound for any d greater than 2. And I would like to remark is, because our bound is field oblivious, on which I will tell you more about, this is somewhat tight, because I already shown an exponential blow up example where s goes to s to the d. So it's somewhat weak, s to the d square log n, but has the notion of exponential blow up in terms of the individual degree. Okay. Okay, so let's go to the proof of sparsity bound. It's really simple. So what do I have to show? F is S sparse. I have to somehow show that G and H are also somewhat sparse. I have to show that G and H are like S to the order D square log n sparse. Okay, but we instead show a slightly more general result. What we show is, suppose G is S sparse and I multiply it. Instead of looking at it as a factoring problem, I look at it as a multiplication problem. So G is S sparse, and if I multiply it by arbitrary polynomial, how much can the sparsity decrease? So what we show is instead that, so if G is like S sparse, and if you multiply by arbitrary non-zero polynomial, the sparsity of S is actually lower bounded by S to the 1 by D square log n, and this will directly imply our factoring result. So in particular, you can interpret this as, instead of factoring question, like that there should not be an overwhelming cancellation of monomial when you multiply a polynomial. And here I am assuming that individual degree is bounded by D.
So this is, we are looking at the individual degree of the factor, not the individual degree of the original polynomial.
Yes, yes. So somehow it's much more general than that. So even if one factor has small individual degree, we are done. Or you can look at it in fancy language, the ideal of G, where G is small individual degree polynomial. Okay. And the proof goes through this Newton polytopes, which was discussed in small details in quite a lot of talks. So okay, so you have a polynomial and you look at its exponent vectors. So for all aij's where aij's are not equal to 0, which is called the support of the polynomial, if you look at the exponent vectors and plot them and look at its convex hull, that is what we call as Newton polytope of a polynomial. It's a very small example. Suppose you have this simple polynomial, you just draw its exponent vector and the Newton polytope will look something like this. It's a really simple example. Okay, but Newton polytopes have really, really nice properties. So the first property is it's well behaved with respect to multiplication. So if you multiply two polynomials, the Newton polytopes turns out to be Minkowski sum. This is a classical fact. And the second fact is, here Vp denotes the number of corner points or the number of vertices of a polytope. They are somehow, and if A is a so if you have a Minkowski sum of, then the vertex are lower bounded by max of the vertex of individual polytope. So I just want to highlight this is a max, not a min, and this is for Floer. Okay. Okay, so just by staring at these two things, you can get a beautiful relation in terms of sparsity lower bound. Okay. So clearly the sparsity of a polynomial is bounded by the number of corner points in its polytope, because you will plot it, number of corner points will be mostly less, cannot be more. And since it's a multiplication, by first it's a Minkowski sum, and by the second lemma, by the second fact, it's bounded by max of number of corner points of individual polytope. So if you notice, like a problem which is completely algebraic, it's translated into a problem of discrete geometry. I just have to count the number of corner points in a polytope to give a lower bound on sparsity. Okay, good. So, okay, to give a slight intuition, so one can say that, oh, so to prove sparsity bound, I have to just look at two facts and somehow what's the motivation? So the motivation comes out to be, if you multiply two polynomials, the main intuition is if a monomial can be written in two different ways, it can get cancelled. And the monomials which can only be produced by just one way, it will not get cancelled. So we somehow look at all the monomials which can be written uniquely, which is somehow captured in this corner points question. Okay, good. So let me revise our main task. G is a polynomial which is n-variate with small individual degree. H is an arbitrary non-zero polynomial, and somehow the question of lower bounding the sparsity of f turns out to be just counting the number of corner points in the polytope of G. Okay, so this will be the main technical lemma now. And I just want to remark that this was already known to Durer and Oliveira, and we just somehow built from that. Okay, so if you have an arbitrary polytope, then it can have, there is no dependence between number of internal points and number of corner points. Why? Because look at this polytope, it has, let's say, few internal points, few corner points, but I can always scale it up. I can scale it up, and now the number of internal points are much more. Looks like they don't have any relation. But notice we can't do this scaling because we have this individual degree bound. So in each of the coordinates we are bounded by d. So we look at something like this sort of a picture. We can't go too far away. And instead of counting the number of corner points in a polytope, let's look at the other question. Suppose the number of corner points are t. How many internal points can I have in this polytope? Which is the same, just the other way of looking at it. So let's say we have t corner points. Let's see how many integer points can I put inside this polytope. So okay, this is a polytope, v1 up to vt are the number of corner points, and these blue dots are lattice points. Why lattice points? Because exponent vector is an integer vector. Okay. So can you somehow relate these two things? Can you somehow say that all these integer points are can somehow be associated with d of these vectors? As it turns out, something very similar is true. So along with each of these lattice points, there's a point very close to it. So epsilon close in the L infinity sense, where epsilon can be thought of as 1 by 3. Such that these green points are actually a small uniform combinations of very few of the corner points. So this was already well known, stated by Birdman, and has a very simple proof. So suppose you have a bunch of vector v1 up to vt, and you pick any point which is in the convex span, then there is so for all these blue points there is a green point which is very close to it, which is a order d square by epsilon square uniform combination. What is a uniform combination? So a uniform combination of a bunch of vectors is just taking its average or looking at its centroid if you want to look geometrically. So okay, so yes.
What is U here?
It's
Capital U. Is it the same as V?
Yeah, yes, yeah. I messed it up. Yeah. Good. So because each lattice point has a very close by neighbor, which is a uniform combination, we can associate each of these lattice points by one of these uniform combination vector. And how many of these uniform combination vectors are there? So these are t to the d square log n, and this directly proves the sparsity bound. So somehow, yes?
U is a subset of V, right? Like you won't always take the average of all points.
Yeah, uniform vector means just an average, and there is a uniform combination vector near each lattice point.
So for each point there is a subset U of V, for which the average is the mu prime one.
But how many such subsets can be if you are just allowed to take d square log n of them, t to the d square log n?
Right, but I don't understand what. So you're taking a combination not of all points, right?
Yes. Yeah, that's what this lemma says. You don't have to go to all points, just a few of them, because you are working in this individual degree regime.
For every internal point, there's a nearby point which can be associated with some subset of the vertices.
Exactly, that's what I'm saying. So U is a subset of V in this notation.
So for every
It
mu in
should
the
be V.
convex span of V, for every mu in every lattice point in the interior, there is a subset. I mean, there's no notation. There's a subset of d square log n over epsilon square vectors,
Right.
which are corner points.
I get it.
Yeah.
Okay.
So the proof is probabilistic for the theorem?
Yes, it's just Chernoff union, just which explain this d square and this log n.
It's probabilistic proof or not?
Yes,
Okay.
it's the Birdman proof is just Chernoff union. Okay, so I'm done with my sparsity bound proof. So factors of sparsity S, individual degree d, are S to the d square log n sparse.
So here you didn't even have, so you go to every point in the convex hull of capital U, and you're saying it can be approximated by a sparse combination of the points in U. It's not even, you didn't even use the fact that these are integer points.
Yeah, no, so not here.
Okay.
But somehow this integer points are used because they are quite far apart, and thus each can be associated with at least one
So
uniform combination.
It's unique, it's the association, you're not taking a whole bunch and associating
Yes.
at the same time. Okay.
Okay, so let's move to the deterministic factoring algorithm. So let me give a brief overview of what is known. So a factoring algo is given a polynomial. Whatever representation you give me, you either give its complete factorization or tell that it's irreducible, cannot be factorized. It's a well-studied problem and has lots and lots of applications. So how do you represent a polynomial? White box arithmetic circuit, black box arithmetic circuit, no need to go in details. So, and for all these models, we know how to factorize. So these are classical results. And all of them are actually randomized algorithm, and a natural question was from a long time, and even now, can we de-randomize these algorithms?
What do you mean by factorized and black box arithmetic?
Oh, good. So if you have a black box of a polynomial, you give me a black box of its factors.
So each factor, give me a black box.
Guessing you just need the notable access.
Yes, yes, yes.
Computer.
Yes. Okay, good. And so, as it turns out, de-randomizing this question of polynomial factorization was actually equivalent to the problem of de-randomizing PIT. So PIT is a problem given a circuit which is poly-size, poly-degree, tests whether if it's 0 or not. And KSS, Koparty, Sharaf-Shpilka showed that de-randomizing PIT for VP, class of poly-size, poly-degree circuits, is actually equivalent to de-randomizing polynomial factorization for VP. So natural question is, okay, we know quite a lot of PITs. Can you do some of de-randomization of polynomial factorization?
This
So
is black box or white box?
this is both black box and white box. If you give me black box PIT, I can do black box polynomial factorization.
It's
If
for
you-
both, black
yes,
box and
works for both. And so one of the main classical result is I can do PIT for sparse polynomial by Cleve and Shpilman. So can you de-randomize factoring of sparse polynomial? This was.
This is a black box PIT for sparse, I guess.
Yes, yeah. And this does not preserve classes. So de-randomizing PIT for class C does not yield a de-randomizing polynomial factorization algo, which I'll give a vague overview why. So if I go to inside the KSS details, also all these algorithms look like this. So there are a bunch of steps. Step 1 requires some randomness R1, step 2 requires some randomness R2. So there are lots of steps requiring different types of randomness. And what KSS showed that you can remove all this randomness by going to a PIT instance. So instead of randomness R1, let's hit polynomial P1 and P2 and P3. So it's these polynomials that should be sparse if I'm looking into factoring of f being sparse. But these polynomials, if you go into details, are actually as hard as determinants. They're like big, gigantic matrices, and we have no clue how to do PIT for these things. So it's really hard directly going to KSS and trying to de-randomize PIT, and thus polynomial factorization. So what we show is we can actually do this, and the time required is s to the d to the 7 log n. So if your d is small enough, we can give a quasi-polynomial algorithm. Here, mod of f means log of the character, poly in characteristic, or the bit complexity if you are working over complex. So we can do this deterministically. Just a remark, this log n factors come just because our sparsity bound has this log n factor. If we can improve the sparsity bound, this will become a polynomial algorithm for individual degree constant.
What is that poly D and
D is the individual degree here.
that?
What mod f, which I just said, mod f means if it's a finite field, it's poly in the characteristic, and if it's rational or something, it's poly in the bit complexity. Just the usual sense, the way we define it.
So univariate polynomials can actually be factored over, say, rationals can be factored deterministically in polynomial time, but multivariate is no longer known, is it?
No, it's randomized, we know, but deterministically it's equivalent to PIT.
Even over zero characteristic?
Yes. Good. So let's give a generic factoring algorithm overview. There is some pre-processing at start, then there is this big hammer Hilberts Ability theorem, and there's this bunch of GCT which is done by solving a bunch of polynomial equations. We take a slightly different approach. It's more like Kartoff and Traeger approach. We do some pre-processing. Again, we go around Hilbert irreducibility by some hack, and then we do reconstruction of our factors, and then we test our factorization. Just an overview. I'll give details. Good. So let's assume, for simplicity, that our polynomial is monic in some variable. So this we can assume without loss of generality, and we can do all these things deterministically. So let's assume it's monic in x1. So since our individual degree is d, which is small, this d is small.
So you can do this transformation to monic while preserving individual degrees?
Yes.
I see.
Yeah, it's all exercise, but can be done just by what was already known in the literature, nothing new ideas. Okay, good. So if your f looks like this, its factorization is looks simple enough. So if f is monic in x1, its factors are also monic in x1, and this gives a really nice thing that there are at most d factors, just because all of these factors will have some term of x1 in it. So which is really important in our analysis. So the number of factors are not too many. Okay, so let's go ahead. So what is Hilbert irreducibility? Hilbert irreducibility said if you are in the randomized world, do a random projection which is from n variate to, let's say, 2 variate, and irreducible polynomials say irreducible. What does that mean? So it preserves the factorization pattern, because if g1 is irreducible, I will go to some g1 tilde being irreducible. So somehow going to less number of variables preserves the factorization pattern. And in deterministic world, well, we don't know any Hilbert irreducibility. So if I try to emulate, if I try to do a variable reduction, maybe this can go messed up. So instead of having 5 factors, my factors can be at most 20 or something. So I don't know, and one can't de-randomize Hilbert irreducibility just because de-randomizing is like hitting some big determinant which we don't know how to do.
So is Hilbert irreducibility just picking a line? And
Yes.
okay.
There are variants of it. That basically, if you project random enough, then irreducible polynomial says irreducible. Line is one variant of it. You can talk about other variants as well.
You want to have 2 variables left at least.
Okay, good. So we don't know how to do irreducibility, but let's say I try to reduce variables somehow and it get messed up, but somehow I can take care of it. What I can do is, because how many factors can it be? As I showed before, they can be at most d many and d small in my case. So I can somehow brute force it. What do I mean by that? I can somehow do a clubbing of all these 20 things. So if I have d many factors, I can go over all possible clubbings of them, which is like d to the d, which is not too much in my case. So I can brute force this factorization pattern. Now you will ask, but how do you know which pattern is correct? And my answer to that is, I don't need to know. At the end, I'll test my factorization. I'll do my factoring, I'll go for all these patterns, and at the end, I'll somehow test my factorization and give the right answer. So before giving more details, I have to somehow tell you this very nice, neat trick of black box of Kartoff and Traeger. So how do you get an oracle access to factors? So this is a very neat trick. So suppose you want to evaluate your factor at this point alpha comma beta bar. So somehow just project it to this line which has somehow hidden in it this beta parameter on which you want to evaluate. What is this b is somehow came from Hilbert irreducibility, which somehow preserves irreducible polynomial to irreducible. So this is some other hack, but now if you factorize this polynomial and if you substitute x equal to alpha and t equal to 1, you will exactly get the evaluation of factor at alpha comma beta. So it's really simple. Okay. So this is the black box trick, and now what do we have is, we somehow after reduction of variable, we have oracle access to all of these. So we can evaluate g1 tilde, g2 tilde and so on. And we also know the clubbing. So we somehow know which of them are associated to g1, which of them are associated to g2. So we have evaluation of g1, g2 and g5. And by my factoring bound, by my sparsity bound, all of these polynomials are somewhat sparse. Since they are somewhat sparse and we can reconstruct sparse polynomial, I'll reconstruct using black box oracle of Kartoff and Traeger, and I'll essentially get my factors back from the oracle. So the remaining step, I'll reconstruct all my factors and test my factorization. What do you mean by test my factorization? So I have f, which I know is sparse. I know the number of factors are not too many, and all of them are individually sparse. and all of them are individual sparse. So this whole system, f minus g1, g2 up to gk, this system is sparse. So I can test my factorization by doing a simple Cleveland-Schmidtman PIT. So this just concludes our factoring algorithm. I'm hiding few details, how to make monic, but those are all simple steps. Okay, so just to summarize, we show if you have individual degree assumption, then factors is s to the d square log n sparse, and if d is small enough, we can give a quasi-polynomial deterministic algorithm. Okay, so I'll give some open problems. The first and natural open problem is, can you improve this sparsity bound? So I gave an example being s to the d, but my bound is s to the d square log n. Can you somehow remove it? Can you make it s to the d, or can you give me an example where the blow up is indeed s to the d square log n? But the more interesting question to me is making it field specific. I somehow believe that the blow up should be just quasi-poly, should be like s to the log s over characteristic zero fields. And that example of finite field just an anomaly, these things should not happen.
You mean that there's no bound on individual degree, for total degree?
Yeah, sure. So can you make this argument field specific? Can you somehow use that coefficients do matter? So can you make it field specific? And the other question is, give a factoring algorithm without the individual degree assumption. So suppose I prove tomorrow that all factors of all sparse polynomials are indeed sparse. Even if we assume this, we don't know how to re-randomize polynomial factorization for sparse polynomials. So just because we have to use that Hilbert irreducibility somewhere, and I don't know of any other trick than just brute forcing over all patterns. So if we don't have this individual degree assumption, even if I assume all factors of sparse polynomial are sparse, I don't know how to do it. And the last question is, actually what my factoring algo gives, or what this whole thing gives, is not a factoring algo for sparse, it actually gives a scheme. So if you have the individual degree assumption, if you can reconstruct the factors, if you have both these two things, then you can factorize. What do I mean by that? So suppose if you assume multilinear ROAP, you have a closure result of factoring, you know how to reconstruct, you have individual degree bound. This will directly plug into that and give me a factoring algo, deterministic factoring algo for that. So for ROAPs, everything works out except I don't know how to prove ROAP with constant individual degree are closed under factoring. I don't know how to prove that. If someone can prove that, that would directly imply a deterministic factoring algo for ROAPs with bounded individual degree. So these are three questions stemming from this, but they are of three different flavors. One is if you are a sparsity fan, one if you are a fan of factoring algorithms, and other if you are a fan of closure results of arithmetic circuit class. So these are three different questions which are very, very interesting to me, and I just want to conclude. Thank you.
Questions? Yeah?
Where is the D7 from in your serial?
What is?
Your result, you have a D to the 7?
Yeah, but that's like some concrete calculation of the factoring algo. We have to like do a bunch of steps, and that is a D to the 7 just because of that. It's not essential, it's just we did the calculation to find out what this exponent was. There's nothing unique to it. You can make it D to the 5.
Slightly like more general question. Say you know about your polynomials that the Newton polytope is saturated, meaning that any integer point inside belongs to the support. So you know, you have that assumption. Can it help you to do the factoring? That again, you know that any integer point in Newton polytope is actually in the support.
So is your question a structural question? So do you want to study the sparsity of factors, or do you want to do an algorithm how to factor these?
For algorithms. And actually for both.
Okay.
But anyway, this property, saturation, did it kind of show up in...
Yeah. So somehow answering all this question will somehow... So this is really an oblivious approach. If you don't care about cancellation, what are the things which can never get cancelled? Those are actually captured by corner points. If you tell me anything inside the polytope, I don't know how to use that assumption.
Some other questions? Okay, let's time.